different versions here. It is given. So actually, you have to by heart all these things. The proofs are not necessary, but you have to know all of these identities. Okay, as like formula, you should know all these things. Then we had this example also. We did this also. Okay. Now today we are going to talk about the application to boundary value problems. So BVP means boundary value problems. So that we call it as the BVPs. So BVP means they are also partial differential equation. They are also partial differential equation. Okay. Now, before we do some exercise on examples on application of BVPs, let's have some theories first. Okay. So here, say we have a function ux comma y. So partial differential equation means we have more than one independent variable. Okay. So we'll say our function ux comma y. This is the unknown function. Okay. Now we are going to consider the Fourier transform of this function. Fourier transform these functions with respect to the variable x. So you can remember in Laplace also, we took Laplace transform with respect to the variable t. So here actually we cannot have Laplace Fourier transform together, in the sense that we can consider only one variable at a time. Therefore, here we are going to consider this one. So, what do you mean by a partial differential equation? For an example, you have an equation like this: da bar squared u over da bar x squared plus da bar squared u over da bar y squared equals 0. This is one example for partial differential equation. Here, the independent variables are x and y. Now, by solving this equation, actually, we are trying to find the unknown function ux comma y. Okay. We want to find this ux comma y. That is said to be solution of this partial differential equation. Okay, right. Now, we are going to define few things. So u bar omega y, because we are going to take the partial differential Fourier transform with respect to the variable x. Okay. Therefore, we are saying Fourier transform of the function ux comma y. Here it is capital, and we are putting in capital. Okay. So ux comma y. These are just notations. You don't need to worry about that thing. Okay. Fourier transform of the function ux comma y equal to, let me write it in this one. So we are saying that the Fourier transform of the function, the unknown function ux comma y equal to u bar. Okay, because actually we are going to have the Fourier transform with respect to the variable x. Therefore, in the place of x, you will have omega. Come on. So that is the Fourier transform of this one. We are taking this one. Okay. Then, then the Fourier transform of remember this one, Fourier transform of DABA n ux comma y, okay, over DABA xn equal to minus I omega to the power n u bar omega y. So this is the Fourier transform of nth derivative with respect to the variable x. With respect to the variable x. Okay. So this one actually you can remember yesterday also I told you. Wait a minute, I'll show that one. Where is that? Yeah, look at here. Yesterday also I told you. This is the one. When you have one variable, okay, so when you have one variable, that is the case. Fourier transform of fx dn xn. Here we are saying derivative because we have only one variable, then that is equal to minus I omega to the power n f bar omega. So similarly, here, since we are having two variables, when we have the partial derivative with respect to x, then that would be equal to minus I omega n q bar omega, this one, in this one. Now, here, this is not the, now we have some assumption here. With the assumption, okay, so this is not just derived, okay, there are some assumption behind this one. Okay, there are some assumptions. That is, u comma DABA u over DABA x comma DABA u over DABA x, DABA squared u over DABA x squared dot comma DABA n u over DABA, sorry, n minus 1, sorry, n minus 1. This all tends to 0 as x tends to plus or minus infinity. Okay, with this assumption only we can have this one. Okay, so this assumption is, without this assumption, this formula is wrong. Okay, so u DABA u over DABA x, that means that partial derivative up to n minus 1. U first derivative, second derivative up to n minus 1 tends to 0 as x tends to plus or minus infinity. With this assumption only, the Fourier transform of DABA n ux comma y, DABA x n equal to minus I omega n u bar omega y. Okay, so this is important. So similarly, so if so, say for an example, Fourier transform of DABA squared u over DABA x squared equal to, okay, minus I omega to the power n, okay, u bar omega with the assumption given that when given u comma da by u over da by x tends to 0 as x tends to plus or minus as x tends to plus. So with this condition only we can write this statement. Okay, here we are taking that the Fourier transform of the unknown function u x comma y is equal to u bar omega y. Okay, so this is important. The second thing, because these are important, okay, these are important, that is why I'm writing this one. Second thing, Fourier transform of da bar n, okay, u x comma y. Now we are going to have the differentiation with respect to y, but our variable is x. But we are going to have the differentiation this way. We are going to have the differentiation with respect to y. Then this is equal to, okay, da bar. Okay, this is equal to you can say d. Say that this is equal to d n u bar u bar omega y over dy. Okay, here you can consider omega as constant. You can think omega like constant. Okay, so very important, you have to understand this one. Here actually we are having the Fourier transform with respect to the variable x. Then when you take the Fourier transform of the function, derivative of the function with respect to y, then this is the one. Okay, so you have to understand the difference. Okay, when we consider the Fourier transform with respect to x only, okay, we get this one. Okay, so with this assumption only we can write this one. Otherwise, it is not possible. Okay, so that is what here they are telling. So here they have written the same for second order. Okay, so second order, if you write this one, we know that it is I omega. Sorry, we know that as I told you, this one is actually equal to minus I omega to the power n. No? So minus I omega to the power n. No? So minus I omega to the power 2. Yeah, minus I omega to the power 2 into u bar omega 1. Here notation is like het, but you put bar, okay? So actually we know that this is I. Yeah. So I squared is minus 1. So this is actually minus 1 minus 1 squared I squared omega squared u bar omega. So minus 1 is plus 1, I squared is minus 1. So minus omega squared u bar omega. Okay, this is how it came. So here you can see that yeah, this one is actually equal to what? This is equal to, if you simplify this one, you will get minus omega squared u bar. Okay. So here the condition is important. That is why they have given the condition. This condition, look at here. U da by u over da by x tends to 0 as x tends to plus or minus infinity. The proof is given here. This is actually Fourier transform. Fourier transform. Fourier complex transform. Okay, Fourier complex transform. Now, what about the Fourier sine transform? So Fourier sine transform da bar squared u over, wait a minute, let's write this one. Let Fourier sine transform of the function ux comma y equal to u bar s omega comma y. Then the derivative fs da bar squared u x comma y over da bar x squared. This is equal to, you have to by heart these things. Huh? This is equal to u s sorry u sorry not us u x comma 0 ux comma 0 minus omega squared u bar s omega y. Okay, so this is Fourier sine transform. Fourier sine. This is normal function. Look at here. Look at the difference. Okay, this one is the Fourier complex transform. Fourier complex transform. And this one is the Fourier sine transform. Okay. Then, say for an example, Fourier sine transform of da bar squared u with respect to da bar y squared. Then this is nothing b squared us omega comma y over dy. Okay, so when we have the differentiation with respect to x only, we are having this one. Okay, similarly we can write the Fourier cos. So before that, let Fourier cosine transform of the function x comma y equal to uc bar omega y. Okay, then Fourier cosine transform of da bar squared u over da bar x squared. Look at the variable. This time we are considering da bar u over this one. This is equal to da bar u over da bar y when y equals 0 minus omega squared u bar omega comma y. Look at the difference. Cosine is ux naught. Here, the derivative of the function with respect to y, and this one. Okay. Derivative of this function. Similarly, Fourier cosine transform. Sorry, here it should be C. Okay. Similarly, the Fourier cosine transform of the function da bar squared u over da bar y squared equal to, as usual, d squared uc omega comma y over dy squared. So there are three different things. You have to understand them clearly. Okay, clearly you have to understand that. This is, here we are considering the nth derivative, Fourier complex nth derivative. This is the form. This is not directly coming. Actually, we write this with this assumption. For an example, if you write it for the second derivative, it will be minus, sorry, it should be 2. I'm sorry, it should be 2. I'm sorry, it should be 2. So minus I omega squared u bar and this one, and if you simplify that one, you will get this one. Okay, and the corresponding, if it is y, the derivative is with respect to y, and this is the equivalent. Similarly, here we are trying it for cosine transform, Fourier cosine transform. Sorry, Fourier sine transform. And Fourier sine transform, the second derivative. Here we are not talking about the nth derivative. It is enough to consider, because you can write it for nth derivative, but here it is enough to consider only for second derivative. So if you consider for the second derivative, it is ux comma 0 minus omega square u bar s. That means that Fourier sine transform of ux comma y omega y. And with respect to y, then that is the derivative of Fourier sine transform with respect to the second derivative of Fourier sine transform with respect to y. Similarly, you can consider cos 1. Cos 1 is this one. Okay. So here I can show that one. This is the thing. So there's a minus here. I'm sorry for that. Right. There's a small mistake in my formula. Please wait a minute. I'll show that one. Sorry for that. Here there's a omega. Sorry. Okay. This is omega ux comma 0 minus omega squared u bar s omega y. Okay. And this one shall not with respect to y, this should be x with respect to x. And minus is also here. That's a minus. Okay. You can think like a formula. Okay. So anyway, you can think like formula here. This is the first, these are the things. These are the things I told you. Okay. So now we are going to do some applications here. Okay. So there are three situations. We can talk about the three situations. Now we have three transformations. One is the Fourier complex transform. We have the Fourier sine transform. And we have the Fourier cosine transform. So now this is the rule, or you can consider this as rule of thumb. Okay, for which transform you should use. If the question comes, the one of the variable in the boundary value problem, if one of the variable is minus infinity to plus infinity, that is, if our x variable is minus infinity to plus infinity, then we have to use the Fourier complex transform. If u0 comma y is known, if u0 comma y is known, depends on the question, you have to choose one of these three. There are three things: Fourier complex transform, Fourier sine transform, and Fourier complex transform. Depends on the question. Okay, you have to choose either Fourier transform, that means Fourier complex transform, or Fourier sine transform, or Fourier cosine transform. Here is the criteria. So here is the note. Okay, if the x variable is minus infinity to plus infinity, then you use the Fourier complex transform. If u0 comma y is not, if u0 comma y is not, then you use the Fourier sine transform. Use the Fourier sine transform. Okay, use the Fourier sine transform. If da by u over da by x when x equals 0 is not, then use the Fourier cosine transform. Okay, now if we'll do some example, then you can understand that one. Okay, right, we'll do the first question. This is the first question. Okay, now if you look at the first question, okay, now we have da bar 4u da bar x4 plus da bar squared u over da bar y squared equal to 0. If you look at one variable, that means our Fourier variable, that is from minus infinity to plus infinity. We don't need to worry about this variable. Okay, we don't need to worry about this variable. Actually, we have to we have to be concerned about the variable that we are going to take Fourier transform with respect. Okay, right. Also, you see that here, u da bar u over da bar x, da bar squared u over da bar x squared, da bar cube p over da bar all tends to 0 as x tends to infinity. Therefore, we can use that condition. We can use that formula, derivative formula. These are actually initial conditions. Okay, these are initial conditions. Therefore, for this problem, actually we have to use Fourier complex transform or simply Fourier transform. That is what here it says. That is what here it says. Minus infinity to plus infinity. Then we have to use the Fourier transform. Depending on the question, depending on the information given in the question, we have to choose the method. We have to choose the method. Okay. Right. So we'll do that part. Quickly do that part. So question number 1 is da bar 4u over da bar x4 plus da bar squared u over da bar y squared equal to 0. We are given that u x comma, how it is given? It is given like u equal fx when y equals 0, da bar u over da bar y equals 0 when y equals 0. So this is the thing. This is what we are given. U x comma 0 is equal to fx. The function is not given. Function is not given, but they have just given function fx. Then da bar u over da bar x when y equals 0 equals 0. Okay. So now solution. So from the since x is between minus infinity to plus infinity. Okay, we will use this is you don't need to write this one, but that is for your understanding. We will use. Can anybody tell me what we will use when the variable is minus infinity to plus infinity? Which transform we will use? We have three transforms. One is Fourier complex transform. The other one is the Fourier sine transform. The other one is the Fourier cosine transform. So which transform we will use now? Can anybody tell me which transform we'll use now? Yes. Now we have to use the Fourier complex transform. So we will use Fourier complex transform. we use the peripherals. So let the Fourier complex transform of the function u x comma. Initially, we have to write this one. Let the Fourier complex transform of the function u x comma y be u bar omega y. Similar to what we did in Laplace transform. We are taking this one. Here, actually, we are taking the Fourier transform with respect to x. Okay, Fourier transform with respect to x. So, if you want, you can write it. Fourier transform with respect to x. Okay, Fourier transform with respect to x. Now, if you take the Fourier transform throughout the equation, so the Fourier transform, okay, da bar for u over da bar x4 plus da bar squared u over da bar y squared equal to the Fourier transform of. So using the linearity property, okay, you can write it as Fourier transform of da bar 4u over da bar x4 plus Fourier transform of da bar squared u over da bar y squared equal to 0. So as I told you, actually the variable here, these two are different. Here it is we want to find the Fourier transform of fourth derivative with respect to x. Here it is second derivative with respect to y. So actually we are here considering our transform variable as x. Therefore, this will become, since it's the fourth derivative, minus I omega to the power 4 into u bar omega y. U bar omega y plus, this is second derivative. No? So with respect to y, remember, with respect to y. So with respect to y mean what? It is nothing but d squared u bar omega y over dy squared equals 0. So for this y, for here one variable is with respect to x, the other one is with respect to y. So when it is with respect to y, we just write this way. When it is with respect to x only, we write this way. Remember here, let me show you again. It is here. Look at here. Second derivative mean minus I omega to the power n here. Nth x with respect to x only, this way. If it is with respect to y, then that is dn u bar omega y over dy. Okay, so that is important. So now, if you look at this one, if you simplify this one, this becomes I to the power 4 minus 1 to the power 4 is 1, I to the power 4 is plus 1. So this becomes omega 4 u bar plus, this is second derivative. That means you can write it as, using the differential operator, you can write it as d squared u bar equals 0. So this is actually a second order differential equation in y, because here the variable is y. Okay, omega is now you can consider as a secondary variable, or you can just consider it as a constant. Okay, so now actually this is an second order ODE in y. Second order ODE in y. So if you write this in this form, you can write this as d squared omega to the power 4 u bar is equal to 0. Okay, so then you can write the solution now using the auxiliary equation. You can write u bar omega y equal to, okay, so you can write it as a cos omega squared y, because our variable is y. Differential equation is in y. Okay, therefore a cos omega squared y. Why I am putting omega squared? Because I have omega to the power 4 plus b sine omega squared. So now I have got this one. Now I want to find out this value of a and b. Okay, so this is the Fourier transform of the solution. This is the Fourier transform of the solution. We have to consider the inverse Fourier transform. Before that, we want to find out the value a and b, the constant a and b. Okay, to find the value, to find the constant a and b, okay, we'll do this one. So now we are going to, now we want to find, this is the procedure. I'm telling the procedure. Now we want to find the constants. I'm slowly explaining. Second one, third one, I will move little fast. Okay, now we want to find the constants. Find the constants a and b. Okay, to find this constant, we will use initial conditions. We'll use the initial condition. We'll use the initial condition. So initial condition is already given here. Look at here. These are the initial conditions. So how to use that one? Now we'll think of that. How to use that one. Right. Now how to use? So we'll first of all, we'll different, because we have only this one, but the initial condition is given for u. Initial condition is given for u. Therefore, what we will do is, we will find the derivative of this one, first derivative. You may not understand why I am taking the first derivative. Later you can understand. So we'll take the first derivative of this one with respect to y. So I am considering, okay, I am considering the first derivative. Du bar omega y over dy. So you can here I am taking the derivative. So that becomes, if you take the derivative of this one with respect to y, then I will get a omega squared cos omega squared y plus b omega squared sin omega squared y. Sin omega squared y. Okay, we will shortly you will understand why I am considering the derivative of this. Okay, because I am going to use the initial condition to find the constant. To find this constant a and b, we will use initial conditions. In order to apply the initial conditions, actually we want to consider the first derivative of this one. First derivative of this one. Now we are having this one. Du bar omega y over dy is equal to this one. Now I am going to consider the Fourier transform of. Now consider You will understand the things. Wait a minute. Now we will consider, or we take Fourier transform for initial condition. Fourier transform for initial conditions. The first one, okay, Fourier transform of u x comma 0. This is equal to integration 0 to infinity. Okay, integration 0 to infinity. Yes, integration 0 to infinity. 0 to infinity u comma 0. Okay, or you can put u comma 0, no problem. E to the power I omega u into d. I omega u into d. Okay, we are taking the Fourier transform of the function u x comma 0 here. So this is equal to, this is equal to u bar, okay, actually u bar omega 0, u bar omega 0, u bar omega 0. So look at here, Fourier transform of u x comma 0 is same as this one. It is same as this one. Okay, but the Fourier transform of u x comma 0 is what actually? Fourier transform of u x comma 0 is what? What we are given? Fourier transform of x comma 0 is what? Fx. No? Fourier transform of this one is fx. Okay, wait a minute, I'll show that one. Yeah, we are taking the derivative first. We'll do the derivative first, then show this one. So wait a minute, I'll like, okay. Sorry, I'm sorry. That also we want to do. This also we want to do. We'll do that later. So now we'll use this one. Wait a minute, I'll show you this one. Sorry for that. Now we have got this, no? So now we'll take the Fourier transform of da by u over da bar when y equals 0. So now we'll use the Fourier transform of da bar u over da bar y when y equals 0. Why I am doing all this work? Because I want to find this a and b. So now see how I am finding this a and b. Da bar u over da bar y. So you can, these are the steps. These are the steps. Okay. So you don't need to change the steps. Okay. So first you find the initial solution, not the initial solution, the solution. Then you use the initial condition. Okay. Here you take the first derivative. Da bar, so d u bar y over this one. This is equal to, look at here, we are using the definition. Since it is with respect to y, since it is with respect to y, okay, so you can write it in this form. du bar over dy. That is why I told you always. Now you know this, no? The Fourier transform of the Fourier transform of this one is equal to du bar over dy when y equals 0. Okay, when y equals 0. But according to this one, we are given that it is 0. According to this one, it is given that it is 0. Here, I'm sorry. Yeah, look at here. Da bar y over da bar u over da bar y equal to 0. Da bar u over da bar y equal to 0. So we are using that one. Sorry, this one is, I'm sorry, this one is da bar y over. I'm sorry, this one. This is y. Okay, da bar u over da bar y when da bar y equal to 0. So we are using this condition. I will explain it again if you have a confusion. Let me use this one. So I'll explain it again quickly. So now we want to find the constant a and b. We want to find the constant a and b. To find this constant a and b, what we are going to do is we are going to use the initial condition. Okay. To apply the initial condition, we are taking the first derivative of this one. Okay, first derivative. So first derivative of this u bar with respect to y, then that is equal to a. Yeah, actually here cos omega squared, no? So if you take the cos, then there should be minus here. To differentiate cos a omega squared. Sorry, this one is sine, no? Earlier also we wrote wrongly. Minus a omega squared sine omega squared y plus b omega squared. When you, if you differentiate sine, it becomes cos, no? Cos omega squared. So this is the correct one. Earlier we wrote wrongly. So du bar over dy is equal to minus a omega squared sine omega squared y plus b omega squared cos omega squared y. First derivative, is that wrong? Which one is wrong? Is it correct now? 77? Is it correct now? Minus a omega squared sine omega squared y plus b omega squared cos omega squared y. Is it correct now? Okay, now thank you. So then now what we are doing is we are considering the Fourier transform. Now take now take Fourier transform of da bar u over da bar y when y equals 0. Okay, so that means that Fourier transform of da bar u over da bar y, because I'm going to use this condition. Now I'm going to use this one. That is why now I'm going to use this initial condition. In order to use this initial condition, okay, I'm considering, because here I have given da bar u over da bar y when y equals 0 is 0. But here actually the function I have is u bar, isn't it? Understand carefully. Here actually we want to find a and b. Now the initial conditions are given for u x comma 0 and da bar u over da bar y, isn't it? Da bar u over da bar y and u x comma 0 is given. But we have actually the Fourier transform of that function. Therefore, we want to convert the initial condition to Fourier transform. So that means that if you want, I can write it here. You can write it. Initial conditions, these are for your understanding. You don't need to include this in your answers. Initial conditions are given for the function u, but we know u bar only. Here, look at here. We have found u bar only. That is why, so we want to convert, or we want to find the initial condition for u bar. Okay, so actually initial conditions are given for u only. In the question, initial conditions are given for u only, but actually the function we are having here is u bar. Therefore, we want to convert the initial condition to u bar. That means that we want to find the initial condition to this one. So u bar mean what? That is the Fourier transform of this function. It's the Fourier transform of this function. Therefore, we want to consider the Fourier transform. So that one I'm considering first, Fourier transform of the first one. Okay, we are considering the Fourier transform of this initial condition, da bar u over da bar y when y equals 0. So this is equal to, according to the definition, minus infinity to plus infinity. Minus infinity to plus infinity. Okay. Da bar u over da bar y into e to the power I omega, you can put x, dx when y equals 0. So here the variable is y, but here the Fourier transform variable is x. Therefore, you can write this as d u bar dx, sorry, dy, I'm sorry. Here the variable is y, no? When y equals 0. When y equals 0. Okay, when y equals 0. But we are given that this one is 0. But we are given that this one is 0. Therefore, this will be equal to 0. Just look at here. We are given that da bar y over da bar u over da bar y when y equals 0 is 0. Therefore, this function is 0. This part is 0. Therefore, this one is 0. So that means that here, if you du bar over dy equal 0 when y equals 0. So this implies, say, if you say this is your first equation, then the first equation implies as, okay, if you put y equals 0 in this one, y equals 0, you get that if you put y equals 0, left hand side is 0 equal, right hand side you get omega squared b squared, sorry, omega squared b equals 0. So this implies as b equals 0. Therefore, now we are having the equation u bar equal to, now we are having the equation u bar equal to minus, so not minus, a cos omega squared. Okay, now a cos omega squared. So b, the value of b we have found. Using this initial condition, we have found the value of b. We have found the value of b. Okay, so that is why here it is given. That is why here it is given. Where is that? Look at here. So this implies as, now if you substitute this value in this equation, you get 0 equal sine 0 is 0 plus b omega squared cos 0 is 1. Therefore, this implies as b equals 0. So now we are putting b equals 0 here. Therefore, we get u bar is equal to a cos omega squared y. A cos omega squared y. So we are having u bar equal to a cos omega squared y. So we have used this initial condition. Now this initial condition is used. We have this initial condition. So for that initial condition, now what we want to do? The second one. Look at here. Here actually we are using this initial, second initial condition. Okay, we want to find the Fourier transform of u x comma 0. This is equal to what? 0 to infinity. 0 to infinity. U x comma 0 e to the power I omega x into dx. We are given that, okay, this is equal to fx. This is equal to fx. So that means that this function is fx. We are given. Therefore, this is nothing but u bar omega 0 is equal to Fourier transform this function, which is equal to f bar omega. Okay, because this is fx, no, this function is fx. Therefore, f bar. So now we have found this one. Here we are finding this one, du bar over d by when y equals 0. Okay, then we are using the second initial condition. So this one is this one. Now what we are going to do? We are going to substitute this in this equation. Now we have u bar is equal to u bar omega y equal to, we have a cos omega squared y. Now I am going to put y equals 0. Then that is f bar omega equal to a. Therefore, my a is now. Therefore, the solution is u bar omega y equal to, my a is f bar omega into cos omega squared y. So this is the solution. But actually, this is in Fourier transform version. So I want to find u. So what I want to do? I want u. Then I have to take the inverse of this one. Fourier inverse of u bar omega y. Okay. So that is equal to ux comma y is equal to integration minus infinity to plus infinity 1 over 2 pi. Okay, 1 over 2 pi, and u bar this one. So 1 over 2 pi u bar omega y into e to the power minus I omega x into e omega. So that is equal to 1 over 2 pi minus infinity to plus infinity. My omega u bar y is this one. F bar omega cos omega squared y into e to the power minus I omega x into e. So that is the solution. That is the solution. So that is what here it is given. The solution is given in this form. So do you understand this? Or you want me to explain once more? Tell me whether you understand, or I will take another 5 to 10 minutes to explain that one, because definitely you will get a question from this section. So do you think that it is better to explain it once more, or it is enough? Tell your opinion, then I can. Okay. So I write the steps, okay? So here, steps. I'm writing the steps. Step one is take Fourier transform to given PD. That is the first step. We take the Fourier transform to given PD. Step number two. Okay, step number two. You find du bar over dy. Okay, find this one. So because of this result, you will get u bar. If you take the Fourier transform, you will get the solution u bar. You will get I'm writing this one. So you will get ordinary differential equation. Solve it and get u bar omega y. This is the first step. Take the Fourier transform of the given PD, then you will get ODE, solve it and get u bar omega y. Step number two. Step number two. Okay. Find u bar, sorry, du bar omega y over dy. Okay, this is nothing. So you just find this one. Here you know this one. Then step number three. Okay. Step number three, first one, find Fourier transform of initial condition. Fourier transform of the initial condition. Find Fourier transform of initial condition find Fourier transform initial condition, this one. da bar u over da bar y equal to 0. Okay. Then find one constant. Then find one constant. Second one, find the Fourier transform of second initial condition. Then find other constant. Last step, step number 4, find inverse Fourier transform. Okay, now we'll do this one. So our function is given u4 over da bar x4 plus da bar squared u over da bar y squared equal to 0. Okay, now what I'm going to do is I'm going to take a Fourier transform throughout the equation. Then if I take a Fourier transform, this is with respect to x, this is with respect to y, then I can write it the answer. I can write if I minus I omega to the power 4 u bar. So before that, we'll say let Fourier transform of u equal to u bar. Okay, u bar plus this one is actually with respect to y. Therefore, this will become e squared u bar over dy squared. Right hand side is 0. Then we will have the equation d squared omega to the power 4 u bar equal to 0. Okay. If we solve this equation, this is a second order differential equation. If we solve this one, u bar omega y equal to, you can write it as a cos omega squared y plus b sin omega squared y. Okay, so this is the solution we have got. Okay, this is end of step number 1. Look at the step number 1. Step number 1, take Fourier transform the given PD, then you will get ODE, solve it and get u bar omega y. So now we have got u bar omega y. So what is the second one? Second one says find du bar over dy. So we want to differentiate this one. So step 2, we want to differentiate this one with respect to y. So du bar over dy is equal to, if we differentiate with respect to y, then this becomes minus a, because when you differentiate cos, that becomes sine, minus sine. So minus a, constant is omega squared sine omega squared y plus here b omega squared cos omega squared y. So this is end of step number 2. Step number 1 is finding this equation. Step number 2 is differentiate this equation with respect to y. Do you understand up to now?
Yes,
do you
sir.
understand up to now? Right. Now step number 3, we have 2 initial conditions. We'll now convert the initial condition. First initial condition is da bar u over da bar y equals 0 equals 0. Using this information, we will find what is du bar y over dy when y equals 0. We'll find this one. Okay, da bar u over da bar y when y equals 0 is 0. This is given. This one is given. Okay, this one is given. Why? Because we cannot use this one, because the function we have is u bar. We want to find a and b. In order to find a and b, actually we are going to use the initial condition. But the thing is, the initial conditions are given for u. Actually, we want this in terms of u bar. Therefore, what we do, we take the Laplace transform for this one. So if you take the Laplace transform, sorry, not the Laplace, Fourier transform for these functions, da bar u over da bar y, when y equals 0, equal, actually this is nothing, minus infinity to plus infinity, da bar u over da bar y, e to the power I omega x dx. I omega x dx. Okay, I omega x dx. So this is nothing but, okay, this is nothing but d u bar over d by y equals 0. But we are given that this is equal to 0. Therefore, Fourier transform of 0 equal this one. That means that y equals 0 is 0. Because we are given here, this function is, this one is 0. The Fourier transform, this one is 0, no? Equal 0 equal this one. So now we have used this one. Now we have found the value, this one is 0. Okay. So that means that when you take the differentiation, this is same. Earlier also we have studied. If you want, you can write this also. Okay, so this is not relevant to this discussion. You can write this one. Say Fourier transform of da bar n y over, sorry, da bar n u over da bar n y equal to, we know that du bar n over dy, isn't it? We have studied this one. So from this one, if it is first derivative, Fourier transform of da bar u over da bar y, when y equals 0 mean, what is this? Du bar over dy when y equals 0. But this one is 0. We are given that this one is 0. We are given that this one is 0. Therefore, this must be 0. Okay, so that is what we are having this conclusion. So now what we are going to do, we are going to put this in this equation. We are going to put that in this equation. That is why we got this one. In step 2, that is why we got this one. Now we have found the value of this when y equals 0. Say, if you say this is your equation, say, this is your equation, say, for an example, 1. Then if you substitute this one, substituting okay, du bar over dy when y equal 0 equal 0 in 1, what we get? We get 0 equal, here look at here, if you substitute here, sine 0 is 0, sine y is 0, sine 0 is 0, therefore this part 0, and here b omega squared cos 0 is 1. Therefore, we get 0 equal to b omega squared. So this implies as b equals 0. Therefore, now we have the solution u bar equal to a omega a cos omega squared 1. We have found the value of one constant. Therefore, the solution is now reduced to this one. Now we want to find a. To find a, okay, to find a, we are given that u equal fx, second initial condition. Second initial condition. What is that second initial condition? It says u x comma 0 is equal to fx. Using this one, we want to find u bar omega comma 0 is what? Because function is, the initial condition is given for u. Actually, we want it for u bar. So we want to have a if we take the Fourier transform of this one, Fourier transform of ux comma 0. So that is equal to minus infinity to plus infinity u x comma 0 e to the power I omega x into dx. So which is equal to u bar omega 0. But we know that this is equal to what? This is equal to given. Initial condition is given as fx. Therefore, this is nothing Fourier transform of fx, a function. Therefore, this implies as if we take the Fourier transform of this fx as f bar omega then u bar omega 0 equal to this one. So now we'll take this one and again we are going to substitute it in this one. Say this is second one. Now substitute f this one u bar omega 0 equal f bar omega into. So what we get, u bar omega 0 equal f bar omega equal, we have a cos 0. Cos 0 is 1. So a. Therefore, we get that a is equal to f bar omega. F bar omega. Therefore, now we know the solution. We have found both a and b. So u bar is equal to now f bar omega into cos omega squared y. But actually we want u. We want u. So what we want to do, we have to take the inverse Fourier transform of u bar. So that is defined as 1 over 2 pi. Okay, 1 over 2 pi 1 over 2 pi integration minus infinity to plus infinity. So this is actually u. U equal inverse Fourier transform of u bar. Okay, inverse Fourier. So that is equal to u bar into e to the power minus I omega x into e omega. So therefore that is u is equal to, sorry. Therefore ux comma y is equal to, because x is, u is the function of x and y, equal to 1 over 2 pi integration minus infinity to plus infinity. Now I am going to replace u bar by this one, u bar by this one. So that is f bar omega cos omega squared y into e to the power minus I omega x into. Now this is the solution. If we know the function fx, because here the initial condition they have given just fx, they didn't give a specific function, they have given it as a fx. Okay, if they give some special function, say for an example 1 or 2 or something, if they give e to the power x sin x or whatever it is, then you can find the solutions. Here we have to stop with this one because we don't know what is fx. Okay, so if fx is given, then we can find the integration of this one. Okay, so the solution is given in the form of integration. Okay, so that is the solution of this equation. Do you understand now? Tell me whether you understand this.
Yes, sir.
Right, fine. Right. Now the second situation, second question, look at here. Here x is greater than 0. X is not minus infinity to plus infinity. Here, if you look at the initial condition, we know ux comma 0. We know x comma 0. And also we are given some other condition. So now if you go to here, if u, sorry, u which is given, ux comma 0. Yeah, here, look at here. We know this one, u0 comma y. u0 comma y. So if we know u0 comma y, if we know u0 comma y, then we have to use Fourier sine transform. In the earlier one, we didn't know u0 comma y. If you look at here, the first example, we don't know u0 comma y. Okay, here actually we know only this. This one is actually u x comma 0. Okay, ux comma 0, and one variable is minus infinity to plus infinity. Therefore, we want to use the Fourier complex transform. Now, in the second example, actually, if you look at the second example, the x variable is only greater than 0. That means that x is less than infinity, greater than 0. Therefore, we cannot use the Fourier complex transform. Meantime, if you look at here, we know u0 comma y also. u0 comma y also. Therefore, for this problem, actually we want to use the Fourier sine transform. We want to use the Fourier sine transform. So Fourier sine transform, so we have to take the Fourier sine transform of this function. So second example, our function is da bar squared u over da bar x squared plus da bar squared u over da bar y squared equals 0. In addition to that, we are given some initial conditions. What are the initial conditions? Actually, this condition is not necessary. These are actually we need. Okay, you don't need to worry about this first condition. Here ux comma 0 is equal to 0. Here look at the y. The range of y is between 0 and y. So we'll write x is greater than 0. Y is between b and 0. Y is between b and 0. Then u 0 comma y. Sorry. U x comma 0 equal fx. U x comma b equal 0. And also u0 comma y equals 0. Okay, so now we want to use Fourier sine transform. How to decide? We cannot use Fourier complex transform for this function. Why is that we cannot use Fourier complex transform for this function? Because if you look at the variable x, that is defined for only half line. Therefore, we have to use either sine transform or cosine transform. isn't it? We have to use either sine transform or cosine transform. If the variable is, the domain is minus infinity to plus infinity only, we are able to use the complex transform. Here, the variable is actually x is greater than 0. Therefore, we cannot use Fourier complex transform. Therefore, we have to go for either sine transform or cosine transform. Now, we have two choices, sine transform or cosine transform. How to decide whether it is sine transform or cosine transform? If we know the value of u0, y, if we know the value of u0, y, then we go for sine transform. If you know the value of daba u over daba y, okay, when x equals 0, look at here. Daba u over daba x, sorry. Daba u over daba x. I'm sorry. Daba u over daba x. When x equals 0 is non, then we go for cosine. Here we don't know this one. Therefore, we go for sine transform. So what we do, we take sine transform. So let Fourier, you have to be careful with the notation. Fourier sine transform of u equal u bar s omega y. We take this one. Now we take Fourier sine transform this function. So Fourier sine transform of daba squared u over daba x squared plus Fourier sine transform of daba squared u over daba y squared. Right hand side is 0. So can anybody tell me what is the Fourier sine transform of this function? What is the Fourier sine transform of this function? We studied here. That is equal to what? Omega u x 0, y u zero y minus omega squared u bar. Where it is coming from? Where it is coming from? Here. Look at here. Look at here. Omega u0y minus omega squared u bar s omega y. So that is what I am writing here. Okay. Sorry, here it should be s. Okay. It should be s. Plus, this one is variable is y, no? Therefore, we don't need to worry about that one. That is u squared u bar s over dy squared equal to 0. But from the initial condition, from this condition, u0y equal to 0. So this part vanishes. This part vanishes, isn't it? Therefore, we have omega squared u bar s minus omega squared u bar s plus d squared u bar s equals 0. So that is d squared minus omega squared u bar s sine transform equals 0. Okay. Do you understand up to now? Tell me whether you understand up to now.
Yes, sir.
Right. So we are getting this one. Okay, now you can write the solution of this equation, that is u bar s equal to a cos omega y plus b sin omega y. Is this correct? U bar s is equal to a cos omega y plus b sin omega y. Is this correct? Tell me whether this one is correct or not. From this one, this is the second order ODE. So how to write the second order solution of second order ODE? Tell me whether this one is correct or not. Is this correct? If you solve this equation, will you get this one? D squared U bar S over this one. Will you get this one? We have already studied differential equations. What is the solution of this equation? Is this correct? A cos omega y plus b sin omega y. Is this correct? No idea. Now, anyway, this is the solution. Now, here actually we don't need to differentiate this one. Why we don't need to? We want to find a and b now. In the earlier one, we differentiated because there the condition was different. Here, we don't have any such derivative condition. We don't have any derivative condition. We have only these condition. This one we have used. We have only these two conditions. Okay, we have only these two conditions. So what we are going to do is, now we know that U bar, now we want to find, this is the A. Now, we want to find A and B. Okay, now we don't need to differentiate because we don't have initial condition in terms of derivative. But we know this one. U 0 comma y. 0 comma what we have? What are the conditions? X comma 0. Sorry. We have U x comma 0 equal fx. But the function we have is U bar. So we want to convert these to U bar omega 0 is what? We want to find this one. Similarly, we have U x comma b equals 0. These are the initial conditions. So we want to find the corresponding initial condition of Fourier transform. So we want to find U bar omega b equal to what? Okay. So for that one, what we do, we know that Fourier transform of U x comma 0, which is equal to Fourier transform of U x comma 0 is what? Function fx equal to integration minus infinity to plus infinity. Okay, minus infinity plus infinity fx into e to the power I omega x into d omega. Sorry, not d omega, dx. Okay, dx. When x equals 0. When x equals 0. So actually, yeah. So this is what? This is nothing. F bar. F bar omega. Therefore, U bar omega 0 equal to this one. Similarly, Fourier transform of u x comma b, that is equal to, the function is 0. Ux comma b is 0, equal to integration minus infinity to plus infinity u x comma b e to the power I omega x into, so which is equal to u bar x comma b. This is equal to 0. So if you want, you can write this also here. So you can say that this is equal to u bar. So now you have found this. Okay. So now if you put this one here, there are two conditions now. We have two conditions now. Okay, we have two conditions. Now we'll put these two conditions in this equation. So if you put first one, that is u bar s omega y equal to, we have a cos omega y plus b sin omega y. This is the equation. This is the solution we got. Now if you put omega y equals 0, if you put y equals 0, this part vanishes. We get a, but u omega 0 is equal to what? F bar omega. So we have got this one, F bar omega. A equal to F bar omega. Okay, F bar omega. So now we'll put B, u bar s omega b. If you put y equal b, then we will get a cos omega b plus b sin omega b. But this one is actually 0. Xb u, sorry, this one is not x. I'm sorry, this should be omega. Okay. So this one is 0, equal a, we have found F bar omega cos omega b plus b sin omega. Therefore, E is equal to minus F bar omega minus F bar omega cos omega b over sin omega. Okay, therefore, the solution u bar is equal to A is equal to F bar omega cos omega y. B is minus B minus F bar omega cos omega b over sin omega b into sin omega y. So that is equal to simplify this one, F bar omega over sin omega b. This one you can write it as sin omega b cos omega y minus cos omega b sine omega y, which is equal to f bar omega over sine omega b into sine, you can write it as e minus y Therefore, now to find the u, actually we want to take the inverse Fourier transform of u bar s. Actually, this is u bar, I'm sorry, u bar s. Everything is u bar s. So this is equal to 2 over 5. 0 to infinity. 2 over 5, 0 to infinity. This one, no? F bar omega sine e minus y omega over sine omega b into sine omega x into. So that is the solution. Do you understand? We check the solution. I'm sorry, I made a mistake here. I'm very sorry. I'm very sorry. Here. Actually, I'm very sorry. I'll tell you again why is that. You want to find this one? No? Yes. Therefore, you have to take the sine. Therefore, this is not. You should have told me that. Okay. So this is actually what minus in not. This is minus into plus into it. I'm sorry for that. So again, I'll explain using this one, considering the time. I'm sorry for that. So now we have got this equation. Look at here. We have got this equation. Okay. Now we are taking the Fourier transform for the boundary condition. Actually, we consider Fourier sine transform. Fourier sine transform. I'm sorry for that. So if you take the Fourier sine transform, we get this one. Actually, that is not u bar s omega t. This one is actually what? Fourier sine transform of the function. Fourier sine transform of the function. I'm sorry for that. This is Fourier sine transform. So US, and this one actually, this one is 0. So this is 0. Then if you substitute it here, we get this one. So this is nothing but Fourier sine transform. Okay. So B is nothing but this one. No? This is Fourier sine transform. I'm sorry for that. So everything is same. Everything is same. Actually, I used actually here. I used E. This is wrong. And range is also 0 to infinity. I'm sorry for that. Anyway, I will explain the next class. I want to finish the class. So